Good morning, good afternoon, or good evening, depending on when you are looking at us. Thank you so much for being part of the Material Business podcast and community. And my name is Monica Hernandez, and I'm your host. And today we have a very special guest, Bernardo. Thank you for being with us today.
Very much, Monica. It's a pleasure for me being part of this podcast, and I'm really excited to talk to you.
Thank you. So, Bernardo Santos is a PhD candidate in material science for the Federal University of São João del Rei. I hope I pronounced that correctly. In Brazil, since 2015, he has been dealing with research on materials and corrosion at the Center of Surface Engineering, Tribology, and Electrochemistry in Brazil. From 2021 to 22, he worked at the Institute of Corrosion and Multiphase Technology at The Ohio University, developing research on corrosion inhibition. Currently, he has moved to Norway, where he is both preparing for his PhD defense and working at the Serum Coating, a company that is the fruit of an academic research that led to make possible the thermal spraying of silicon carbide. Thank you for being here. That was quite an exciting and different worlds that you have been in, from Brazil to US, now Norway, and but congratulations. It's at your age, and I was just telling that before. It's nice to see younger generations, pursuing their dreams and flying. It's really amazing.
It's a quite a journey since I started like in the academia and dealing with corrosion. But yeah, here we are.
Awesome. Congratulations. So let's dive right into it. So, what did inspire you to be on this realm of corrosion, localized corrosion, carbon steel pipelines? Why is this a concern that we want to take a look at?
Yeah, so starting from the corrosion general perspective, when I was in the mechanical engineering course, I had this. It was not a mandatory course, but I had the corrosion course, and I was really interested on that because I could see like that it was playing an effect in every single thing in our lives, even though we were not maybe not paying so much attention of it. So I figured that corrosion was a serious problem, and it was in some way also exciting to understand and to study about it. So I started pursuing like some opportunities during the bachelor for uh, doing research, undergraduate research, and that's when I started really studying and doing research on corrosion. So since it's one of the probably the greatest concerns in the industry that we have nowadays regarding the materials, the facilities, the integrity of the facilities, it's something that excites me working with and researching and like trying to find new solutions, studying everything. So it's a very I think the best word to describe it's exciting. It's exciting area of the material science, and yeah, and so everything that all this passion led me to pursue this whole journey.
Interesting. And yeah, you have said very key points on how much money we spend on trying to fixing things that we could have fixed at the design. And we have said it in the last like 10 podcasts, I guess, or all of them, I guess, is we need to make better design, better decisions at the design stage, and that we get to that with the data that we have after we do these kinds of studies and the research that you're doing. So it is very important to pay attention to that. So going a little bit more into like the real world experience, like can you give us some examples of real world experience of the kind of consequences specifically due to localized, because I know you have worked a lot on localized corrosion.
If you don't mind, I will share some of the some real situations that we face, that we may face, mainly when we are talking about localized corrosion. So localized corrosion, as from people that are from the corrosion universe, is everybody knows about it, but we can understand that as we can say that it's the most dangerous mechanism, corrosion mechanism, that are consuming materials, metals in the industry everywhere. And why this is so dangerous, because localized corrosion is differently from the uniform corrosion that corrodes laterally. It corrodes vertically, so it can be a potential cause of failures on pipelines or in any kind of structure, and it can be driven by different mechanisms. So for my PhD, I focused on that, but I'll get to that later. But when just to give a perspective of the real world, how the industry can suffer for these kind of corrosion mechanism. I found this one of the many accidents, unfortunately, but this in particular was the investigations led to the conclusion that localized corrosion was one of the key factors that led to this accident. That was in the early 2000s, that when a gas pipeline failed at some point because of localized corrosion. And then it started, the rupture of the pipeline caused it to start, a fire to start, and that led to unfortunately 12 people were killed in this accident. And just that's one of the matters. Of course, lives are really important, and we have like many operators around the facilities everywhere. So, but another perspective for the industry, economically speaking, is the financial loss that this accident caused. That it was around $1 million in repairs and everything that the company had to deal after the accident. So this gives us a really good perspective of how corrosion in general can be very it's a severe problem, but localized corrosion in particular, it's something that might be undetectable at some point, and it's depending on the models that you're using, but it can be sometimes untraceable, and that makes it even harder for us to understand and to see and to take the correct measures to avoid this kind of problem.
Absolutely, absolutely. So I'm sure a lot of the people that follow us and that listen to us, they understand perfectly the difference between the general and the localized. But you have said it in a way that it's the first time I see it that way, and it's absolutely truth. The general corrosion goes vertically and horizontally, sorry, and then the other one goes into the depth of the thickness of the material. So that's a good way of putting it in simple terms on the difference. So you can imagine how difficult it is to find out that you have that mechanism. For sure. So go ahead.
No, I was just because I always try to. I understand that most of the audience will understand like the basics of what we are talking about, but I always try to deliver the message in simple terms, because one thing that I since I started in the academia and also moving to the industry is that I think it's important for us to try to communicate to people outside of this corrosion universe, because some of the measures that are in the daily lives of people, they can be taken by any people, and some of the people, they also have dealt with corrosion at some point in their homes, but since it's not something that it's spread out in a easy way to understand, I think people get like away from these kind of topics, and it's hard to discuss sometimes. But that's why I think it's the more we try to give a better description of it in the easiest way, I think it's very important.
And I think you're doing it really beautifully because it really is simple and then you can understand it. Sometimes we get tangled into the technicalities and we love
Yes.
MIC and then stress corrosion cracking and SCC and HICAN, so HICAN, all those things and terms. But when we are trying to bring more awareness, which is what we're trying to do here, making it simple just makes a difference. So yeah, that's a really good point. Thank you.
Yeah.
So I know you've worked really hard and just published a paper, and that was a really good, documentation, has a lot of interesting information in it. It also highlights the role of galvanic coupling and propagation of pH. How is that all work together? Can you explain that phenomenon and how that occurs?
So, yeah, just going back again, like I said, like localized corrosion, it's the most dangerous. We can say that type of internal corrosion, mainly when we are talking about oil and gas industries. The pipelines may be submitted to this kind of corrosion mechanism depending on the environment, and but one thing is corrosion, localized corrosion initiation. It can be initiated by different things, but another thing that it's uh, some way, mainly when it's regarding carbon steels, it's less discussed, or there are less approaches to it, is the propagation of existing pits. And the focus of my PhD research was on that, on this subject, the propagation of this localized corrosion. And uh, even though this mechanism, these pits, they can propagate in different because of different parameters. One of the common ways of having this kind of propagation is due to what you said, the galvanic coupling that is established. And how is that in more detailed? We can assume that the usually on carbon steels, the pit is surrounded either by corrosion products or corrosion inhibitors, molecules that are absorbed on the surface. So usually what happens is that the area in which the pit is being corroded, it tends to have a lower potential locally. Of course, if we consider as a whole pipeline, it should have the same potential. But locally, when we are talking about local phenomena, it has a lower potential compared to the surface, the surrounding areas in which it is covered with corrosion products or corrosion inhibitor. And this difference in potential, as we know from the theory, and we have an electrolyte for the electrons to flow. So it is established a galvanic coupling between these areas. And what will happen is that the pit will tend to be consumed, and then the localized corrosion will increase and can cause severe failures. So my my study was focused on using corrosion inhibitors to mitigate this galvanic coupling that was established in this local area of the pipeline. So yeah, we had the problem, but how to get to it, because it's the propagation of localized corrosion. It's very hard to be simulated artificially in the lab. So in the past, in the literature, there was like several studies that uh, used different electrodes. So they were preparing one electrode to act as the cathode of this electrochemical cell. That would be the area covered with corrosion products or corrosion inhibitors, and the other electrode would be what they used to call the artificial pit, and promote this galvanic coupling using two different electrodes. But that raises a lot different challenges, because you depending on the conditions you're trying to simulate, you may need to use different cells, glass cells. It might lead to ohmic drop during the experiment. So there were some concerns, and we decided to have a different approach on this matter. That since we thought that since we have a difference in potential. You have a shift in potential between the area that is your pit, your localized corrosion, and the surrounding areas covered with corrosion products or inhibitors. There is a technique that we can simulate this shift in potential that will consequently lead to a current flowing. That is the potentiostatic technique. And that was what we did in this first stage of my PhD, was simulating uh, uh, propagation of localized corrosion using the potentiostatic technique. Just to recap, the potentiostatic technique is so you can apply a potential to your working electrode, and in consequence there will be a current flowing. And that current could be interpreted as the current flowing in this local galvanic coupling that happens on the pipeline. So having that, we could our main idea was to applying different potentials to simulate different environments that localized corrosion could propagate. So you could have a surface around the pit covered with iron carbonate that would lead to one difference in potential between the pit and the surrounding areas. You could have had it with the surrounding areas covered with corrosion inhibitors that would lead to another difference in potential. So we applied different sets of potential using the potentiostatic technique and injected the inhibitor to the environment, because the inhibitor will naturally tend to absorb to the active surface of the pit, that in this case is our working electrode, and that the corrosion inhibitor would mitigate or not. So our parameter was, if the current that we observed after applying the potential, if it after the injection of the inhibitor, if it starts dropping, it means that the inhibitor is absorbing on the actively corroded surface, corroding surface, and that would tell us that inhibitor for that particular environment, the inhibitor was able to stifle, to mitigate the propagation of localized corrosion by this galvanic cell that is established. So that was basically the understanding that we had, and we were fortunately we published it recently. So it's I like it. It's fruit from my PhD. So for me, it's really important. I'm really proud of it. And just to summarize what we the main findings among many others is that we figured that the capacity of the inhibitor to absorb on the surface, so to mitigate the propagation of localized corrosion because of the galvanic coupling, is dependent on the current flowing. So we observed that there will be a threshold in which the inhibitor, the current will be too high. It will be higher than the absorption mechanism of the inhibitor to the surface. So uh, the inhibitor has a limit when it's facing a high dissolution rate. That it's usually what's happening on the pit. And another thing that we figure is that for some of the conditions that we have investigated, the concentration of the inhibitor is quite important for it to be able to stifle or not. So depending on the potential that you are facing on this galvanic cell, because usually when we are dealing with corrosion inhibitors, we tend to use the concentration that is called the surface saturation concentration for inhibitors, and that's the optimal concentration that you will add to your system that will lead to the lowest corrosion rates with the lowest amount of corrosion inhibitor. But what happens is that for when the material is corroding at the corrosion potential, that's just the OCP, what we call, right? But when you're polarizing the surface, you're artificially increasing the dissolution rate of that sample, right? So that value for surface saturation concentration of the inhibitor is no longer reliable, let's put like that. So depending on the condition that you are in doing this kind of experiment, you may need to increase the concentration of the inhibitor. So those were like let's say the main findings. And one unexpected finding that we found out is that the carbon content on the metal substrate that you're testing is detrimental for the inhibition, the effective inhibition, because we figured that whenever you corrode severely your sample, you end up revealing the iron carbide on the surface, and the iron carbide might lead to poor inhibition. So that was something that we were not counting, when not even expecting. Of course, that's research, and but that was surprising, and that makes a lot of sense, mainly considering everything that was written and published in the literature.
That's very interesting. So taking it from the lab, the research and development and your control conditions to industry, what do you think will be the message to, or the considerations that industries can take or can keep in mind when you just mentioned the selection of, the materials? I guess that's one of them. But
Yeah.
what are other considerations maybe when we are selecting our inhibitors or any regular sampling we need to do? Like, what can industries take away from this in a practical way or a solution? What do you think?
Very interesting question, because I think for every research that we are doing, I usually expect it to be applicable in some degree to the industry. And I think the one of the messages that this research gave is that the when we are doing the selection of the corrosion inhibitor, making the correct selection of it, I think it's very important, because of course, you need to understand the kind of phenomena you're having, and then that would lead you to make the correct selection. But the correct selection of the corrosion inhibitor is important, because we have out there several kinds of corrosion inhibitors. Some are they are retarding the anodic reaction, others are retarding the cathodic reaction, others are retarding mixed, so both reactions in different extents or to the same extent. So that's very important, because that plays a significant role on the potential of your sample. So for instance, if you consider a mixed corrosion inhibitor that retards the anodic and the cathodic reactions to the same extent, there will be a slight or no change in the OCP of your sample, of your working electrode, because the OCP tends to oscillate, to change when you add the inhibitor, whether the anodic or the cathodic is retarded more or less. So when you see that, depending on the application you're having, in this case, you have a shift in potential. You want to overcome that shift in potential. Maybe I'm not 100% sure, because we haven't tested that, but there is a strong high potential that you may not be able to stifle that mechanism, even though the inhibitor might be absorbing on the surface. But that goes back to the fact that, depending on the condition, the inhibitor would not even absorb to the surface. So making the correct selection of corrosion inhibitors, it's really important. And the second thing that I think it's the key in this cases, in this kind of situation, is that investigating the aqueous condition, or I'm talking about the water chemistry, like what kind of ions you have on your environment, what kind of contaminants. That's really important, instead of just looking at the material that you're using, or the corrosion inhibitor, because even with the best corrosion inhibitor, if you have a harsh environment with water chemistry conditions that are not favorable for that inhibitor to perform, it may fail. So having these two things in mind whenever dealing with localized corrosion propagation on carbon steels, I think, are the most important, from my understanding on this matter.
And I think what you have said is just right on point. What some people forget sometimes is that these processes are dynamic. conditions change all the time. And we might be pumping water with certain characteristics today, but tomorrow those are not the same. So that's where, testing becomes really important, and understanding what those changes bring to the place, because it's not the same when your plant is brand new that after a while, when you have already deposits or you have had some failures that induced something into systems, and those are carried out throughout the plant. So understanding that this is a dynamic process and we need to do the retro, like engineering, re-engineering and rethinking and reanalyzing if these conditions that we once predicted are still applicable, or if we need to change something. And that is exactly, and I just spoke with someone yesterday about the MOC processes, the management of changes, and that is exactly when that comes into place at the right time. Is my process the same? Is my condition the same? Something did changed? And if it did, then I need to adjust. And it's no different that when you're driving, right? If you drive in your summertime, it's, different driving than if you're in winter. And we were talking about the winters in these Nordic northern territories of that we're living in, and it's absolutely different. And what do? You adjust, you change your tires, you have your thing to clean up the ice and snow, and it's a different, even the freezing fluid that you put into the wiper is different. So we are used to that. So we just need to translate that into having processes that back up what we are saying here. Is it's important to look at every single parameter. So our things that we selected and predicted are accurate, because it might change over time.
No, I agree 100%, and I do think that I know that the industry takes a lot of measures and it's cautious with all these matters. But I think it's sometimes it can be a huge mistake taking for granted, like, oh yeah, this is what we have. Oh yeah, this, no, you don't need to check it. It's the same process, it's everything. But because, like you said, things change, and things are changing every time, so it can be very dangerous if you just take it for granted and assume and continue taking the old, let's say, the old measures that we were taking, and not being updated all the time and monitoring. So yeah.
Awesome. So in your research, you said that there is need, for further investigation. So what are those opportunities for further understanding on what is next?
So yeah, research, like any other, is like infinite. uh, I mean, if you stay there, I could have done my PhD in 20 years just doing research. There would be endless, and but there are some particular parameters that I think are very important and will deliver a good message, or it will give very beneficial results. That one of them is uh, investigating different kind of inhibitors. So in this particular study, the inhibitor that we used was a commercial inhibitor one. So as we from the corrosion universe, we know that these commercial corrosion inhibitors, they are usually like a cocktail, a mix of different compounds. But this inhibitor in particular was primarily midazolinum based. So that's one of the group of the most common inhibitors, but there are several out there that can be tested, and I think you will deliver a good message in terms of the chemical dependency on this mitigation of localized corrosion propagation. So I think this is uh, one of the future research that I'm more interested into seeing people doing elsewhere. I couldn't do it, but I know for sure that there will be other groups researching on that. And also the second thing that I think it's also important, it's to improve the understanding that we have in terms of the desorption mechanisms of the corrosion inhibitor, because like I said, at some point the current that flows on the surface of the working electrode of the carbon steel is too high that the inhibitor does not absorb on the surface. But there is another a situation that may happen. That is, whenever you have already the surface covered with corrosion inhibitor, so the inhibitor is already absorbed on the surface, and you may suffer some kind of I don't know, oscillation on the potential, or even being polarized, and that inhibitor will dissolve from the surface. So it's a similar understanding. It's not the same thing, but it's similar to what we see with stainless steel with the passive layer. That there are several works, even using the potentiostatic technique, or the post electrochemical tests that investigate this repassivation thing with the stainless steel. But for the carbon steel, whenever we use the corrosion inhibitor, we don't fully understand why the inhibitor may be dissolved by electrochemical forces and then reabsorbed on the surface. Let's say if you make a cycle, polarizing and depolarizing the surface. So that would be interesting in terms of understanding more about the theory behind what we call the desorption potential. That we assume that after a certain potential or a certain current, the inhibitor will fully dissolve, or at least would partially start dissolving from the surface. So I think there is a lack of understanding in this matter, and I think it would be really interesting if people could dive into it.
There's some ideas for the ones that are searching for research topics.
Yeah, there you have.
There you are. Bernardo, time has flown so fast. We are at the end of our time here. Do you have any last message for the audience, for people that are listening to us, and what will you say to them?
Yeah, so first of all, I would like to thank you again for having me, and it was a really good experience being able to talk about my work. But I think for people that are hearing us and they are interested, if they are not already in the corrosion universe, if they are interested in corrosion is a really exciting topic. It's material science. You're dealing with material, you're dealing with the environment, you're dealing with energy transition, you're dealing with several very hot topics that we have nowadays. And I think it's really good to have more people involved, and like you said, new people with exciting ideas, because our universe needs that. And I would be an advocate of supporting people and making them more interested in this matter as much as I can, because I love this matter. It's something that I'm really into, and I hope that we could have more people involved and supporting, and mainly new people, supporting new people to get into this universe. And I think if you're really into it, if you're really interested, you will succeed for sure, because it's a really good area. It's a good really universe for you to dive into.
It has a lot of opportunities and
Yes.
a lot of challenges that are yet to be resolved. So definitely we need more of us.
Yeah.
Bernardo,
Unfortunately,
thank you so much.
yeah. Sorry.
Sorry, go
No,
ahead.
no. I was just going to mention that there's an analogy that it's interesting. That's corrosion is like corruption. You cannot extinguish it, but you can reduce it. So let's do it.
It's very interesting. Every time when we do the podcast, sometimes we have to do lots of addition of the word corrosion, because normally it will translate it in the transcript as a corruption.
Yes.
So it's not only an analogy, it happens.
Yes.
So anyway, for everyone that is listening to us, thank you so much for being here. If you are on like just listening in Apple Podcast or in Spotify, Bernardo has shown us some slides. So if you want to take a look at in our YouTube channel, you can look at the slides as well. And we thank you very much for being part of our community. Bernardo, thank you so much for your time. Congratulations on everything that you have achieved, and I can just imagine what else you will achieve in this, because you're very passionate and you really, it shows that you like what you do. So congratulations for all that passion.
Thank you very much, Monica.
Okay, I'll talk to you soon, and then everyone else will see you in the next weeks with another episode. Thank you so much for being with us.